All right, so hello and welcome to this video tutorial for RC Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 3 here, which is asking us determine the tension developed in cables AB, AC, and AD. So to tackle this problem, first of all, we're working in 3D space. And one thing that I notice off the bat with this problem is that we have two forces of interest here, the tension in AC and the tension in AD, which are acting in all three dimensions, right? They're acting in the X, the Y, and the Z. And the way that we can break these forces down into their constituent X, Y, and Z components is different for each one. So for AC, we've got this kind of two triangle idea going on. And for AD, we have what are called coordinate direction angles, okay? Let's decompose AC first here. So I've just kind of expanded this diagram just to show what's going on here. Now, when we see this kind of two triangle idea that we've got for AC, one way to look at it is essentially to look at this line here and to almost treat that as if it's what we call the XY component, or it describes how much the tension in AC is acting in the XY plane. So let's call it AC subscript XY. We can also look at this line here and almost treat it as the Z component of AC, so let's call it ACZ. We can look at this line here and treat it as the X component of AC, so let's call it AC subscript X. And we can look at this line here and we can treat that as the Y component of AC, okay? Now, when we look at it in these terms, I'm going to trust that you guys are familiar with this idea on the top right. We can effectively say AC XY is equal to cos 60, or AC cos 60, okay? AC cos 60. And ACZ, we can say, is equal to AC sine 60. Now, we can look at ACY and ACX, and note we have a 30-degree angle here. So we can say AC X here is equal to AC XY sine 30. Okay. Now, we've determined ACXY, or we've expressed ACXY earlier. We've expressed it as AC cos 60. So what I'm going to do is I'm going to say that this ACX is also, or we can also say it is equal to AC cos 60, since AC cos 60 is the same as ACXY, sine 30. Okay. So now we have a nice kind of convenient expression for the X component of AC there. And we can use the same idea for the Y component of AC. We can say that this is equal to AC cos 60, since that's our XY component, AC cos 60, in this instance, cos 30, okay? I hope that makes sense to you guys. So we've broken AC down there. Let's go ahead and break down AD. Right, hang on. So we've broken AC down there. Now, you might be thinking, well, let's go ahead and break down AD as well, since that's the other force that we've got acting in all three dimensions. I'm going to take what might be a slightly unorthodox approach here and move straight to resolving in the X, Y, and Z directions, okay? And we are going to use this idea that I've shown on the right-hand side here. So I talked earlier about coordinate direction angles. So the coordinate direction angles, we have alpha, we have beta, we have gamma, which describe the angles with the X, Y, and Z axes respectively. And we can describe the costs of each of these angles as the kind of respective component over the magnitude of the force, or the overall magnitude of the force. Okay. Now, when we resolve in the x, y, and z directions, hopefully it will become clear how this idea can kind of tie in. So let's go ahead then and resolve in the z direction. The reason why I'm starting with the z direction is because we've got this 300-pound force acting down. That's a known value, so it might be quite useful for our calculations here. So we can say the forces in the z sum to 0, so things acting up are equal to things acting down. What have we got acting down? Well, we've got that 300-pound force acting down. What have we got acting up? Well, we've got the z component of AC, which we expressed earlier as AC sine 60, right? So we can say AC sine 60 is acting up. And we've got the z component of AD, right? Now, the angle with the z component here is 45 degrees. That means our gamma value here is 45 degrees. So on the right-hand side of our equation here, we could say the z component of AD. So we could say ADZ here. And we note this idea here. Okay, so the cos, in this case, of 45 degrees is equal to the z component of AD over AD. We could rearrange this. We could say, therefore, ADZ is equal to AD cos 45, right? So I'm going to rub that out, that ADZ idea, and just replace it with AD cos 45. I trust that makes sense what I've done there. We have a nice equation here, having resolved in the z. Is it solvable? No, we've got two unknowns in there, AC and AD, so let's just go ahead and move on. Let's resolve in the x direction, so we can say the sum of the forces in the x are equal to 0, so what's acting towards us in the x is equal to what's acting against us. What have we got acting towards us? Well, we've got AB there, the tension in AB. What have we got acting? I almost omitted the x component of AD here. Now, in this case, we note that alpha here, so the angle with the x-axis, is equal to 120. So we could carry out a similar procedure to here. We could say the cos of 120 is equal to ADX over AD. Therefore, ADX is equal to AD cos 120. Okay, so we can add to our left-hand side here what's acting towards us. We can add AD cos 120. Okay, so we can see how actually these coordinate direction angles are quite convenient for us. Okay, so that's what's acting towards us. What's acting against us? Well, we've got the x component of AC acting against us, and we calculated, or we expressed earlier, that as AC cos 60 sine 30. So we can say AC cos 60 sine 30. Okay, so we have two equations here. We have three unknowns, AB, AC, and AD. Let's move on then and resolve in the y. So we can say the sum of forces in the y are equal to 0. Therefore, things acting to the left are equal to things acting to the right. What have we got acting to the left? Well, we've got the y component of AD, which I'm going to trust you guys understand now we can express as AD cos 60, since 60 is the angle with the y here. Things acting to the right, well, we've got the y component of AC there. We've expressed that earlier as AC cos 60 cos 30. So AC cos 60 cos 30. So we have three equations here, our z, our x, and our y. We know this is solvable because we have three unknowns, A, B, A, C, and AD, and three equations, okay? So how would we go ahead and solve this? I'm just going to scroll down here. One thing that I've noticed is that we can simplify one of our equations. So when we look at our y equation here, note that we can divide both sides by cos 60, so we can eliminate the cos 60s there. And that is going to leave us with AD is equal to AC cos 30, which is a really convenient idea here. Since we're just expressing one unknown in terms of another unknown, we can take that and let's substitute that in for AD into our first equation here, which will then leave us with one unknown, just AC, which we can then solve through for. So when we substitute that in for AD here, we're going to be left with 300 is equal to AC sine 60 plus AC cos 30 cos 45. Now we can factorize our right hand side. We can say this is equal to AC brackets sine 60 plus cos 30 cos 45. And we can then divide both sides by this bracket to just leave AC as the subject. I'm just going to scroll down here. So we can say, therefore, AC is equal to 300 over, let's just put this in brackets to be clear here. So sine 60 plus cos 30 cos 45, which when we bung in our calculator gets us a value of 202.9. We're working in pounds here, aren't we? 202.9 pounds for AC. Okay, so we've got AC there. This then enables us to solve for AD using this idea here. So we can say, therefore, AD is equal to 202.9 cos 30, which when we bung in our calculator gets us a value of 175.7. So we have AD, we have AC. It just looks like we need to solve for AB here. The only equation that contains AB is our x equation here. So what we could do is we could take that AD cos 120, subtract it from both sides of the equation, and then just substitute our values in for AC and AD. So I'm going to take this I'm going to say AB is equal to AC cos 60 sine 30, except we know AC here is 202.9, so I'm just going to write in 202.9 cos 60 sine 30. And remember, we're subtracting this AD cos 20 from both sides. We know AD is 175.7 pounds, so we can say plus 175.7 cos 120 here. And we have a nice big kind of sum here, which we can put into our calculator. Sorry, I meant to write in minus 175.7 cos 120 there. And when we put that in our calculator, we get a value of 138.6 pounds. Okay, so these are the solutions to our problem. If you have any questions or comments, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.